This is problem number 9 on the practice problems for test number 3. Suppose that you receive $1,000 every year and deposit it into an account that earns 3% interest compounded once a year. A, if the first $1,000 comes in today, how much money will there be in the account 1 year from today after interest is calculated and the next payment has been made? Your answer will be most helpful if you do not simplify it. Okay, so first we need to come up with some formula that captures this idea, compounded once a year. So the simple formula that we need is just P times 1 plus R to the T. It's not compounded continuously, so don't use PERT. It's also not compounded like twice a year or monthly, so we're not going to use the more complicated version of this with the ends in it. So that's our formula right there. And let's see if we can do this part A. So $1,000 comes in today, and we want to let that $1,000 grow for a year. So $1,000, and then it's going to grow for a year. So 1 plus the interest rate of 3%, 0.03, and it's going to grow for 1 year. So this is really just 1,000, put the 1.03 first. 1.03 times 1,000. I'm not going to calculate that, I'm just going to leave it. That's the amount of money from that first deposit, but then separately, we make a second deposit. So there's the first deposit, and then the second deposit that happens just today, so it doesn't have any time to grow, is just $1,000. And so then the total is the money you had from your first deposit plus interest, plus the $1,000 that you just put into the bank before we answered this question. Part B, how much money will be in the account 2 years from today? Again, assuming the same kind of thing. Interest is calculated and we've just made, or we just received 1 more payment. So the idea here is that you're going to take this old principal and you're going to multiply it by another 1.03 because it's going to grow for another year. So you can distribute the 1.03 to that. Another way to think of it is to look at, again, splitting up the payments. So let's do it this way too. So we got the first payment, we got the second payment, and the third one has just happened before we answered this question. So the first payment has 2 years to grow. So that's going to be a 1.03 squared times 1,000. That squared is because it had 2 years to grow. The payment we made last year has been growing for 1 year, so it's 1.03 to the first times 1,000. And then finally, the payment that we just received today was a straight 1,000, and it didn't have any time to grow yet. So then the total is the sum of those 3 things. Okay, and then we move to part C, write a formula using summation notation for the amount of money in the account n years from today. So this formula right here is 2 years from today, and notice that the 2 is the highest power right there. So then it seems like we're going to be playing the same game, but we just need it to get up to n years from today. And so we're going to use summation notation. It sure feels like all of the terms in that series up there are of the form 1.03 to some power. Now oftentimes we use n, but we don't want to use n here because n is the variable for the total number of years we're waiting. So how about we use something else like I, and then it gets multiplied by 1,000. Every term in that purple series looks like this. And then what's the starting value of I and what's the ending value of I? So the starting value of I is the smallest I that you see. Here I is 2, here I is 1, here I is 0. So this series starts at I equals 0. And we're trying to wait n years from today. And we saw that when it was 2 years from today, 2 was the highest power. So if it's n years from today, then n is going to be the highest power. So we're going up to n. Part D. How much money would be in the account 11 years from today? Use the formula we discussed in class to answer this question. So if you didn't want to use a formula, you could just do the brute force calculation, something like this, but keep it going up here to 11. And then add up all of those terms. Better is to use the formula, and I'm going to insist on the test that you use a formula. So first we need the formula. This purple series is a geometric series. So we've got 2 geometric series formulas. There's the infinite one, which is simpler, and then there's the finite one, which is what we need. So the sum of the geometric series, a formula that we had was this: a times 1 minus the common ratio to the n plus 1 divided by 1 minus x. Okay, and sometimes it's confusing because there's an n in this problem and there's an n in the formula. I'll just say that this is the number of terms. I don't care what we call it, but the power that we need to put on the x is always equal to the number of terms. So in the purple example, there were 3 terms. N was 2, but there were 1, 2, 3 terms. If n is 2, indeed this gives us a 3 up here. So the formula is going to work. In our case, we need to go 11 years from today. So that's the value of n. Let's plug everything in here. A is the first term. That's 1,000. 1 minus the common ratio. We kept multiplying by 1.03 in this series. When n is 11, n plus 1 is 12. And then we divide by 1 minus the common ratio. So this is what we need to calculate. So let's do that now. Certainly expecting some number more than, let's see, 11 years from today means 12 deposits. So we've got 12,000 that's been deposited plus all the interest that's come in. So let's just do this very carefully. 1 minus 1.03 to the 12. Parentheses around that. Divided by, and then we'll just do the subtraction in our heads on the bottom. And I think we've typed this in right. So we're looking for something over 12,000. Oh, we did not type that in right. We were very close. The subtraction on the bottom is a negative 0.03, which gives us positive 14,192. Which seems reasonable. Again, we had $12,000 deposited plus 11 years of interest, so 14,000 and change is in the ballpark.